Hello. In previous lectures, I described packets of neuronal activity, and today I will show you some code how find such packets and how to analyze such packets in your data. So how to find those packets. So just to remind you, what are those neuronal packets? So if you have activity of many neurons recorded simultaneously, then you can find that activity is not continuous but rather divided in bursts. And it seems like each burst has some similar sequential organizations, that some neuron starts earlier and some later. And this is spontaneous activity, and when we present tones, the organization is very similar. So neurons which tends to start spontaneous bursts are also more likely to start stimulus evoke packets. So the cartoon illustration of this, it would be here, that we have this separate burst and more or less similar sequential order. But when brain is desynchronized, so it is in case when brain is more engaged in activity, then activity in neurons seems to be more continuous. But with careful data analysis, we found that even here during this desynchronized brain state, activity is also not continuous but rather divided in bursts, and the illustration of cartoon illustration of this is here. So we see that the also burst of activity with similar sequential order as during this synchronized brain state, but because those bursts occur so close to each other, those sequences starts overlapping, and it gives this impression of continuous activity. So today I will tell you how to use MATLAB to find some repeating patterns of activity in your data, and what are the advantages of methods used as described in this presentation. Okay, so here is MATLAB code to generate some artificial data. First, we will need to start by generating some, we will not do our examples on real data, we will rather do it on generated data because it will be easier to understand and have control of over the data. So the advantage of working on generated data to test some data analysis methods is that if you are looking for some patterns, then in generated data you exactly know where are the patterns, because by design we will insert at certain times repeating patterns, so we can test our method, how good our method is at finding those patterns. So to generate our data, here I specified what is the duration of data in milliseconds, how many spikes each neuron will fire in this period. Also there is a parameter for fraction of correlated spikes, and I will talk about it later in more details, but basically it is telling if it is closer to 1, then those patterns are easier to spot. If this is closer to 0, then those patterns have a lot of random jitter and are much more difficult to detect. And the last parameter is just number of neurons which we will be simulating. And we will put our data in this array where it will have one dimension, it would be number of spikes, and other dimensions it would be duration of data. So in this array As you see, it is 20 by 100,000 in this data. If there is 0, there is no spike. If there is 1, there is spike. So maybe first let me generate this data to show you what it produces, and later I will explain more details. So if I run it, now I will get this picture. So here you can see that at certain times there are those sequences inserted in data. So there is some random spikes, but there is those clear sequential patterns of activity. So how it is done? Well, here I'm taking that the times of first neuron, it will be always beginning of such a sequential pattern, and here will be loop for generating spike times of all other neurons. So this loop starts from neuron 2 and till neuron number 20. So here we will generate this random spike times of spikes. So it will be, as specified here, 2000 numbers. And here what we will do, this is a little bit complex line, but basically here we are generating a fraction of spikes which will be locked to this times of the first neuron. So here this f, it is this fraction of spikes, so 70% of spikes will be locked to this first spike, and the rest of numbers, so it is number of spikes multiplied by 1 minus this fraction, so it is only 30% of spikes will be occurring at some random times. To make those sequences a little bit more difficult to detect, I also added to those sequences some random jitter. So here I'm generating some random offset that if this neuron fire and this other neuron is in sequence, those spikes, they will not be in the sequence right after it, but they will have some freedom to be either 1 millisecond, 2 or 3 milliseconds, so they will have some time jitter after this spike. So they will not occur exactly at 1 millisecond, they will occur with some 1 millisecond plus some jitter. So this line will generate, will combine those spikes which are time locked to patterns and some additional random spikes. And also what we will do is that we will generate some random data. So we want to compare as our algorithm performs on detecting spike sequences on this data set, but also we want to compare how it would perform if there would be no sequences, if there would be just random spikes. So here we will generate some spike time shuffle data. So here it is a similar period of time showing with time shuffle data. So here you see that those neurons are clearly showing some sequences. Here neurons are firing at random times, and over period of entire data set, number of spikes for this shuffle data is the same as number of spikes for this original generated data. So how we generate this shuffle data? We are just basically shuffle times of each of those. So here we are creating these arrays with spike times. So whenever there is 1, there is spike. And here, instead of putting it at specific time, we are just assigning some random times to those spikes. So it is exactly the same data taken from what we generated, just here spikes are put at random times. And this is this array spk sh shuffle data. One point to note is that here it is very clearly visible those patterns, and those are nice sequential patterns. But when we are recording data, it is quite an arbitrary way how I arrange this data. If neurons would be, for example, arranged in a different way, so here what I'm showing is exactly the same data as here, but instead of plotting neurons from those which are the earliest active till the latest active, so here you see that neuron 20 is usually firing on the end of sequence and neuron 1 is firing on the beginning of the sequence. Here I shuffled order of neurons. So for example, you see that this neuron was firing right here, and now it is assigned neuron number 7. It was number 17 and now is 7. So it is exactly the same data, just the order of neuron is shuffled. So now it is much more difficult to see that there is some patterns of activity, but nevertheless it is exactly the same data, just not sorted by spike latency in those patterns. And the methods which I will show you, it works equally well if we plot neurons in this way or if we have neurons in this way. So it means that the method which I will describe to you, it will able to detect that some neurons fire earlier during burst of activity and some neurons fire consistently later during those bursts of activity. So I will be comparing what is the activity of one neuron in relations to activity of some activity of all other neurons. So in such case, if I look, for example, at activity of this neuron in relations to this other neurons, even if this is the order of neurons is scrambled, it will still show me that usually this neuron is firing later in this burst, later than other neurons, similarly as here. So basically what I'm trying to say is that here, just for visualization of patterns, I sorted neurons by latency to better see those patterns, but when we record data, we don't know which neurons should be, how neurons should be sorted, which should be plotted first and which should be last. And the analysis which I will show, it will help to unreveal if there are some consistent patterns of activity, if there are those bursts of activity, and if neurons are firing at some consistent times during those bursts. Okay, so actually what here is another useful piece of code which plot rasters. So this what I was showing here. I was using command image sc. It is very convenient to plot arrays, and here this is array with zeros and ones. So wherever there are ones, they are shown in green. But sometimes it is more convenient to plot data as a raster, so it uses this plot command. So here each spike is plotted as a line. So it is exactly the same data as shown here, but I use now a different plot command to show this data. And the reason why I have this second command is that if I, for example, want to take this, import this figure to use this for publication. Then it is much more convenient to copy such a raster plot into, for example, Adobe Illustrator, and then make this figure for publication rather than have this in this bitmap. Okay, so in this raster comment, we are taking data from the first 300 time bins from this data which we generated. And here we are looking, we have here a loop for each neuron, and we are looking where are the spike times of those neurons. And here, if there are some spikes, if this vector x is not empty, so this is negation operation, so it is checking if it is empty, and here I'm saying if it is not empty. Then in this case we will plot this line for given neuron at the time when it occurred. Okay, so we have this generate data, and now let's try to see how to analyze it. So the analyses are very simple and straightforward. What we will do is we will calculate cross-chorogram between activity of one neuron and activity and some activity of all other neurons. So we will have loop for each of those neurons, so we will take each of those neurons individually, and we will calculate its cross-chorogram with sum of activity of other neurons. What we will get in this way is by looking how skewed is cross-chorogram, it will give us information if this neuron is firing on the beginning of sequence or on the end of sequence, or somewhere in the middle of the sequence. If there is no sequences, if this neuron is firing in non-party, there is no any relations between activity of this neuron and population activity, then the cross-chorogram should be more or less flat. So it will means that there is no packets, no bursts. So by looking at those cross-chorograms, it will help us to see if there are some bursts and if there is some consistent timing of those neurons within those bursts or packets of activity. Okay, so let's run this code, and later I will explain details. Okay, so what this code did is was calculating, as I said, this cross-chorogram between each neuron and population, and here I'm plotting those cross-chorograms within some time window within plus minus 40 milliseconds. So as you see, the first neuron is the cross-chorogram peak is earlier, the last neuron cross-chorogram peak is later, so each line it is cross-chorogram of one neuron with population. So it shows that in our data this method indeed found this consistent patterns of activity. And now how to quantify it, this sequential order. So one way to do it is that we can calculate what is the center of mass of this cross-chorogram. So we can plot this cross-chorogram and look what is the center of mass. And illustration of this is it can be found in this publication. So 3 years ago we had this neuron paper, formation and reverberation of sequential neuronal activity patterns evoked by sensory stimulation, and we apply exactly the same analysis methods to find packets, and so for each of those cross-chorograms, so here is example of a cross-chorogram. We calculate what is the center of mass within certain time window of this line, and I will show you, I will give you code which is calculating center of mass of cross-chorogram. And if cross-chorogram is skewed more to right, the center of mass will be here. If cross-chorogram is skewed to the left, the center of mass will be there. And it can be, for example, also as a latency measure. You can also calculate what is the position of maximum of this cross-chorogram. But the problem with maximum is that usually cross-chorograms are a little bit noisy, so sometimes peak can be here, sometimes by chance this point can be the highest, so it will add some jitter. Now if you look at the center of mass, it is much more stable measure of neuronal latency. And in this particular paper, what we found is that when we apply tactile stimulation, we evoke some sequential activity, and the patterns of those activity were similar to patterns which occur spontaneously before stimulation. But after we apply the stimulations for 20 minutes, we could reorganize spontaneous activity, that now those spontaneous sequences after stimulation were much more similar to stimulus evoke activity. And interestingly, this only happened in this activated brain state, which is when animal is attentive. When brain state was synchronized, inactivated, it was, for example, when animal is in deep sleep, then we couldn't induce this reorganization. And here, how we measure this reorganization, it was looking how those sequences are changing. So by analyzing what is the latency of each neuron in relation to activity of other neurons, we could find, we could quantify what was the sequential order of spontaneous during spontaneous packets, what was the sequential order during stimulation, and how it was changed during spontaneous activity after stimulation. And if you look in this paper at supplementary materials, so this is those supplementary materials. What you can find is this whole section describing in details those analysis of sequences and latencies. So here it starts by showing how the activity, how we test this latency measure by generating this spiking sequences. Here we generated data with much bigger jitter. So here, if I wouldn't plot those circles around sequences, it would be difficult by eye to see that I inserted sequences here, but nevertheless method was able to detect that there are those consistent sequences. And usually when people look at relations between neurons, they look at cross-chorograms between all pairs of neurons. So instead of looking at activity of one neuron in relations to population activity, they rather look at cross-chorograms between neuron 1 and 2, 1 and 3, and so on, between all possible pairs of neurons. So if we have, let's say, 100 neurons recorded simultaneously, then it would be around 100 multiplied by 100 divided by 2 possible combinations. So it would be a quite large number of this pairwise cross-chorograms. And what we showed here is that by looking at this cross-chorograms between single neurons and population activity, we can get a better estimate of those sequential patterns as doing the standard pairwise correlations. And here is example of cross-chorograms between two pairs of neurons. And the reason is that if we do pairwise cross-chorograms, then there is less number of spikes to calculate cross-chorograms, and it gives more noise and more difficulties to estimate those sequences. Here, by summing up activity of all neurons except one analyzed neurons, now we have much more spiking activity to correlate cross-chorograms, and it gives much more robust measure of those sequences. And here it is what those plots are showing, that if we try to estimate by latency measure what was the timing in sequences, it was quite good estimate for this very noisy data, but from pairwise cross-chorograms it was much more difficult to figure out what was the sequential order. Okay, so how we do those analyses exactly? Here on the beginning I defined some smoothing kernel that we will do some smoothing cross-chorograms, but I will mention this in a few seconds. So the main thing is this loop, that this is loop for each neuron. So for each neuron we are defining what is the activity of all other neurons. So here we are saying that all other neurons are from neuron 1 to, in this case, up to 20. And here, by this empty brackets, we are excluding from this multi-unit activity the analyzed neuron. So later when we calculate cross-chorogram, we are calculating cross-chorograms between this one particular neuron and sum of activity of all other neurons. So here this particular neuron is excluded from activity of what I call all other neurons. And when using this X-core functions to calculate cross-chorogram, we can define what is our region of interest. So we are interested in this short-term relations between neurons within, let's say, plus minus 50 milliseconds. So we can define that only this, in this case, plus minus 40 milliseconds is of interest. We are not interested how neurons are interacting, let's say, at 1 second time scale. And we are repeating the same for shuffle data. So to compare how our method works also on shuffle data, where it should not find any sequences, because in shuffle data there are no sequences. So we do exactly the same cross-chorogram on this shuffle data. And later what I mention is that to better estimate, we are smoothing data with a Gaussian kernel, and here it was defined this Gaussian kernel, so it had standard deviation of 2, so 2 milliseconds, so it is quite narrow standard deviation. So it just make cross-chorograms look more smoother, easier for visual examination. And after the cross-chorogram is calculated, here I'm applying function called latency, which is calculating center of mass of each cross-chorogram. And here I normalize each cross-chorograms between 0 and 1, and it is just helping to find better this latency. Here is this simple function which is normalizing any data I give as an input between 0 and 1. So it takes minimum, subtract minimum from the data and divide by maximum. So its data which is as an output of this function is always between 0 and 1. And latency function is calculating the center of mass of cross-chorogram, and again it's quite simple, and you can try to play with that. Okay, so what we will have as an output of this, as I said, we'll have those cross choreograms, and here what I plotted is the latency found for each of those neurons. So each cross choreogram is centered on 0. So here in this plot, first neuron is plotted on the top. In this plot, first neuron is plotted on the bottom. So it shows that the latency of the first neuron is around -9 milliseconds. So it shows that this neuron on average is active around 9 milliseconds earlier than the rest of population. And the last neuron, neuron number 20, is on average active around 8 milliseconds after entire population. So we found that in this our generated data, this latency measure can discover that there are those bursts of activity and what is the order of neurons. Now I will also demonstrate that it works if we, for example, decrease quality of those sequences. So here, for example, I change this fraction of correlated spikes from 0.7 to 0.2, so only 20% of spikes are participating in those sequences. So it is much more difficult by eye to see where are those sequences. So it is one sequence here, one sequence here, one sequence here, one here, here, and here. So sequences always starts where it is this first neuron active. So if I wouldn't know about it, it would be very difficult by eye to find those sequences. But when we run those analyses, we should discover it, and now those cross choreograms are not as clear as before. You see that it is less crispy, let's say, but nevertheless, if we look at the order of those neurons, although that there is quite a bit of jitter, it's still possible more or less to uncover what is the ordering of neurons. So in such data where it is very difficult to see any order, any bursts, with those analyses is still possible to discover that there seems to be some sequential activity patterns. And to show it example for shuffle data. So for shuffle data, you can see that those cross choreograms are much more random, that you don't see any clear peaks for any of neurons. So it shows that in this that this method is not finding sequences where there are no sequences. Only where there are some sequences we can find some reproducible cross choreograms and calculate latency. And as I mentioned, this method was used to not only find latency, but it was very useful to compare latencies, those sequences between conditions. So for example, if there will be no any sequences, what we would expect is that for spontaneous activity before stimulations, there would be, let's say, if we sort it, we will find that by chance some neurons were active earlier, some later, but it should have no relation what will be the order of neurons after stimulation. So after stimulation should be completely different order of neurons if there wouldn't be any sequential activity. But because the latencies before and after are strongly correlated, we found that it is indication that spontaneous activity has this sequential order, those organized packets. And more importantly, comparing the latencies during stimulation, we found that this during stimulations we have very similar sequential order as during spontaneous activity, and that repeated stimulation is causing brain to reorganize, that spontaneous activity after stimulation is reverberating those stimulated patterns and is reorganizing to better represent stimuli. Okay, so I will finish this. One last part is that in this supplementary materials there is also quite a bit of description of this latency measure and how we are using it, but also there is on the end some MATLAB code showing how to reproduce figures in this manuscript, and how this latency latency compares, for example, to template matching analysis, and probably Masami Tatsuno or David Houston will talk more about template matching analysis. So here you have some code how to do template matching to compare with latency analysis. But basically most of this code which is here in the supplementary materials, it is just put together those three pieces of code which I presented. So I will also put online this other code, how to generate figures from our supplementary materials, and you can explore in more details those sequences analysis. And again, thank you for listening, and if you have any questions, feel free to email me, or we can talk during seminar sessions. Thank you.